Welcome to week 4. First, we are going to focus on 10.7, which is inscribed and circumscribed polygons. So, the first thing we're going to talk about are a couple definitions. So, a polygon that is inscribed in a circle, okay, I'm going to box off that word, is all of its vertices lie on the circle. So, you will notice in this first, we have a triangle inscribed in a circle, a quadrilateral inscribed in a circle, a pentagon inscribed in a circle. Notice that it has the word in because those polygons are inside the circle. Okay, so that's one way it could be written. The other way it is also described is the circle is circumscribed about the polygon. So these two expressions mean the exact same thing. So I'm just going to jump down to the bottom for a second. You'll notice that there's these two definitions. So that definition is going to also go along with this one, which says the center of a circle circumscribed about a polygon is the circumcenter of that polygon. So you'll notice I labeled A, B, and C. The circumcenters would be A, B, and C in terms of those specific diagrams. Okay, the next type of definition we have is when you have a polygon that is circumscribed about a circle. Okay, so this time the polygon's on the outside. All of its sides are tangent to the circle. So what's happening here? You basically have a hat theorem situation going on all around the circle. Remember those walk around problems? Just like that. So you've got all these congruent tangents. Now, again, just like above, if I was to say, let's see if I could draw these really tiny. If I was to say that the circle is inscribed in the polygon, those two mean the exact same thing. Now, when we have a polygon circumscribed about a circle, we call that center. So for instance, O, the incenter of the polygon. Okay, so the name of the center depends on which figure is inside which. Okay, so remember, inscribed, the figure is in the circle. Circumscribed, the polygon is around the circle. So why is it important that we know what circumscribed and inscribed means? Well, Theorem 93 actually ends up happening when we have polygons that are inscribed in circles, specifically quadrilaterals. So if a quadrilateral is inscribed in a circle, its opposite angles are going to be supplementary. And we call a quadrilateral that can be inscribed in a circle a cyclic quadrilateral. So this right here, quad ABCD, is a cyclic quadrilateral. So how can we prove that this cyclic quadrilateral has opposite angles that are supplementary? Well, first of all of these angles are inscribed angles. So let's say I want to focus on A and C and prove that they're supplementary. Well, A is going to be half the measure of its intercepted arc, which is BCD. And angle C is going to be half the measure of BAD. So if I wrote out the measure of A plus the measure of C should in theory be half of the measure of BCD plus half the measure of BAD. Now, if I rearrange this a little bit, I could distribute out the half, and then I would have arc BCD plus arc BAD in the parentheses. And what do I know about those two arcs? Well, BCD goes to here, and BAD goes all the way to here. So together, the two of them actually add up to 360. And what is half of 360? 180. So now we just proved that the measure of angle A plus the measure of angle C should add up to 180 degrees. And we can do the same exact proof for B and D. The last theorem that is in this section is Theorem 94, and that is if a parallelogram can be inscribed in a circle. So if we know, for instance, that this quadrilateral was a parallelogram, then it must be a rectangle. That would mean that the diagonals of that rectangle would be the diameters of the circle, and you would be able to use the Pythagorean theorem to find missing pieces. So these are all the theorems and definitions that are part of 10.7. Now we're going to do some practice. So using the diagram at the right, see if you could find the following 4 pieces of information. So first of all, the measure of angle B and the measure of angle C come from Theorem 93, which says that the opposite angles in a quadrilateral inscribed a circle are supplementary. So for instance, if this is 95, then B is opposite that, so that's 85 degrees. C is opposite angle A, so that must be 70 degrees. So subtract from 180. Now, divide the measure of arc BC. You'll notice that you have these 2 congruent chords. So that means if this is an inscribed angle A, which intercepts this whole entire big major arc BCD, then that must mean this whole entire arc is 220. But we know that congruent chords intercept congruent arcs. So if this whole thing is 220 and these are the same measure, then each of these is 110 degrees. And I only knew that because of the congruent chords. For arc ABC, that is an intercepted arc for angle D. So I have to take 95 and double it, and I will get the measure of angle ABC to be 190 degrees. Now see if you can answer the final practice question. An equilateral triangle, that's important, the equilateral, is inscribed in one circle and circumscribed about another circle. The circles are concentric. Remember, concentric circles means that they share the same center. If the radius of the smaller circle is 21, find the radius of the larger circle. So when you have an equilateral triangle, you need to remember that 30, 60, 90 triangles can be formed by dropping down this altitude, or this apothem, whatever you want to call it. And then that is also my radius of my smaller circle. So I knew that that was 21. Then I drew in this dotted line to represent the radius of my larger circle. So I created a right angle. Now, if this is an equilateral triangle, this radius bisects here and makes this 30 degrees, and we have 60 degrees here. So there's my 30, 60, 90. If the radius is 21 and that is across from the 30, then that must mean that the hypotenuse is 42. And the hypotenuse is also acting as the radius of the larger circle. So your answer was 42. So those are your notes for 10.7. Now you can go on to your 10.8 notes.